Hi, in this video, I'll be talking about GPU or graphics processing unit. We all have heard that GPU accelerates AI model training significantly. And we might have heard that this is because GPU enables faster and parallel matrix multiplication. Where exactly is this matrix multiplication happening? What exactly is GPU doing to accelerate AI training? And before all of that, you may have heard of graphics card if you have played games. And is the GPU same as graphics card? GPU was originally meant for enhanced gaming experience, but then later its use case nowadays is primarily found in AI model training. So this video is about the entire story about GPU. We will also take a numerical example of how exactly GPU performs a calculation in gaming especially, and how did all of this end up making NVIDIA the most valuable company on the planet. So let's get into the video. Even if you don't know much about GPUs, you must have heard that GPUs make computations very fast and they're also quite expensive. So let's have a look at what does a modern GPU look like, how big is this, and how expensive is it. So this is NVIDIA Tesla A100. It's probably this big, around 26 centimeters in length, 11 centimeters in width, and 3.5 centimeters in depth. So it's not a giant unit. Like, it's not something that fills a room. Many people may have such a visual about the GPU, maybe because they have not seen it. And this particular unit is like $8,000, $10,000. You can buy it on Amazon also. So this is an example of a GPU, but there are more powerful GPUs. The GPUs that we are talking about today in large language model training is maybe $10,000, $40,000 expensive. So the graphic card that you may have heard of in the context of gaming, this was very popular when I was playing games in probably 2008, 2010. My classmates, they used to buy graphics card to have a better gaming experience for FIFA, GTA Vice City, GTA San Andreas, etc. So, but I never tried it myself back then. It was, I think, 6,000, 7,000 rupees at that time. But basically, graphics card is not exactly same as GPU, but graphic card consists of GPU. It's one of the components. GPU is one of the components inside graphic card, but it will also have like a cooling fan, VRAM, etc. But essentially, graphic card, you can say that the primary component of graphic card is GPU itself. So the original product that NVIDIA was selling was these gaming accelerating units like graphic card. It provided the gamers an enhanced gaming experience. So we'll see how exactly GPU was able to do this. So, when NVIDIA was building this, they probably did not envision AI to be the biggest use case, because ever since deep learning happened, the training of neural networks essentially was consisting of many matrix multiplications. And the same matrix multiplication was also involved in gaming graphics. So that is the reason why NVIDIA was quickly able to adapt to AI. When AI became a big thing, training AI in a much more faster way became a very lucrative thing to do after 2010. But let's first look at gaming graphics. How exactly did GPUs revolutionize gaming? And this was very popular even in the early 2000s. So in gaming, let's say you are playing a 3D game, you have basically objects placed in a scene. You will have trees, maybe it's a shooting game, you have the gun, you have whatever environment you are in, you have all those 3D objects. So each 3D object in a game is described by a set of vertices. So vertices like this, these are what I call as vertices. And the way these vertices are connected with each other is through triangles. So these vertices will make a a group of 3 vertices will make these triangles. So these are all the vertices. And let's say the object is this cube, then there are these triangles. So the entire object is made of these triangles. And these triangles can construct any kind of polygon. So here the polygon that it has constructed, like the shape it has constructed, is like a cube. Each face here is like a square. So the triangles can construct any complex shape, and the more the number of vertices you have, the more the number of triangles, and the more the number of triangles, more finer your model will look like. So you must have seen games definitely which had very poor resolution. So if this is a complex shape of a monkey, the rendering of this monkey happens primarily in the form of vertices, the vertices that are connected as rectangles, and then the rectangles will have color, it will have texture, it will have shading, etc. So if you really look at a game, something that looks like this is a very high resolution game. An individual scene like this can have 3 to 4 million vertices that are being rendered at a given time. In the game, you just need to render those vertices that are coming in the field of view of the camera. Vertices outside of the field of view of camera are not necessarily to be processed. So, but even within the camera field of view, you will have these many number of vertices, maybe 2 million, 3 million vertices. And there will be a similar number of triangles, like 3 to 4 million triangles created by these vertices. Now, these triangles, which will form, and since these are very, very, very small triangles, you won't even see them as triangles in this particular scene. The triangles are not noticeable at all, which is why this game is probably very difficult to run on a cheap computer. But basically, there will be even thousands of colors and different textures. So textures, as in you can superimpose the texture of a brick or the texture of a wood, something like this, on top of the vertices. If you have worked in Blender, you would know how to add these textures. And on top of all of this, there will be a light source. Sometimes it will be an artificial light source, like a indoor bulb. There will be multiple light sources here and there. Sometimes if it's an outside environment, there will be only one light source, which will be like a virtual sun. So in this case, it's just a virtual sun. And then this light source will also have light rays coming and hitting on the objects, and it has to reflect based on the texture, based on how far the object is from the light source, etc. And each of these scenes are refreshed maybe 60 times a second. The frame rate is 60 frames per second. So every vertex in this scene has to be rendered 60 times in every second. So there are a huge number of calculations going on in just rendering this scene. Don't even think about physics at the moment. Here we are not even talking about the physics of, let's say, a bullet hitting someone, or let's say a car colliding with another car in the game. Those are physics, but here we are just talking about the rendering of the graphics, which is primarily processed by these graphic processing unit. You may have also seen games where the details are maybe less attractive. I mean, this game looks very beautiful, I'm not denying that, but you can see that it's like a low poly. The surfaces are low poly, meaning low number of polygons it has. So the number of vertices in this game is probably not 2 million. It's maybe 1/10 of that, or 1/50th of that. And there are games like this also, which have low graphics. It's easy to run on pretty much any computer because the amount of calculations that the computer has to perform is much lesser. So now the question is, what calculations is a computer performing when rendering a scene like this? What exactly is happening to vertices in a scene? And how does it relate to matrix multiplication? And how can GPU help in this whole process? So we are going to look at that from a very specific example. So if we have a scene, right? So if the game is a 3D game, the objects in the game are 3D, but finally when it is rendered in front of you, it's getting rendered on your screen. Your screen is 2D. It has a bunch of pixels. So each pixel has some color. So the 3D object is somehow converted into a format on your screen, which is 2D, such that you will still feel like what you're seeing is very realistic. So this involves a few different steps. So firstly, individual objects. So let's say in your scene, you have a tree. So when people make these games, the objects can be made separately. A car can be made separately. A tree can be made separately. A person can be made separately. And then later, all of them can be brought together into one single game scene. So individual objects have their own origin. So if I am making a car to be inserted into a game, I'll make the car separately, and the car itself will have a local origin. And then every vertex that will form part of the car. So car will be made of like a mesh, and every vertex in this car will be having a local coordinate system with respect to its own origin. But then when this car is placed in an actual scene, it will have a certain size with respect to rest of the things in the scene. Maybe the car is a toy car. Maybe the car is an actual scale car. So we have to calculate a few things for the car when we place it in the scene. So we have to calculate new coordinates. So these coordinates are different from the local coordinates that the objects have, for the vertices have. So here, what coordinates are we talking about? Are we talking about the coordinate of the entire car? Of course, but in what format? In the format of coordinate of individual vertices that form part of the car. Then if we are placing the car with a certain rotation, maybe in the original coordinate that the car alone was built, maybe it was aligning along the x-axis. But maybe when we are placing it in the scene, there is some rotation. Maybe the car is placed on a hill. So there will be rotation along all the three axes possible. And then there should be some scaling. So if the car is, let's say, a smaller model of the car we are placing as a toy car in the scene, or if the car is far away from the camera, some scaling has to be applied to the car to make it appear smaller or bigger to your eyes in your screen, in your computer screen. So, and then of course, scaling also works with respect to positioning of the camera. So if the camera is farther away, the object is scaled down. Otherwise, the object is scaled up. So there are two types of scaling. One is scaling the object itself. So if you have a small water bottle versus big water bottle in a scene, you can have the same model placed in the scene, but one will be scaled up, one will be scaled down. And then finally, after calculating all of these coordinates, of course, you have to convert it into a 2D format, because all these objects will have three coordinates, X, Y, Z coordinates, because that is how we build the 3D models. But then finally, when it is rendered onto your screen, it will have only two coordinates, which exact pixel values are making up that object. So this process is called rasterization, which is converting the XYZ coordinates of the object into just XY coordinates to be rendered on a 2D screen. There are a few more details like ray tracing. So if there is a light source, you can basically trace the ray such that you are calculating the number of bounces. If you have worked in Blender, you can define the maximum number of bounces that the ray tracing has to do. And this will actually make the whole object look much more realistic. So ray tracing is a very important thing that these game graphics perform to make scenes look very realistic. And on top of all of this is just rendering the visual. There has to be proper physics involved. Some games have very good graphics but very bad physics. Some games have good physics but bad graphics. I'm sure you have played this, but very rarely games have excellent graphics and excellent physics, right? So it's very difficult computationally. Now let us look at a particular vertex. So let's say in this scene, let's say this is your scene. This is where you're looking from, and your screen is your computer screen. And on your computer screen, you will see things as 2D. Nothing is 3D. But in reality, all the objects that are modeled originally, they are in 3D. So somehow, and in that 3D model, there are vertices, and then you can see that the vertices are making many small triangles. Even this sphere is actually consisting of triangles. The more the number of triangles, the more smoother the sphere or more smoother the other object is. Now let's consider, and here is a light source also, this white sun. So now consider just one vertex, this white dot. I have enlarged the size of the dot to make you see the dot. But basically just consider this vertex, and you are looking at this vertex in the game scene. And let's say the vertex has XYZ coordinates with respect to the global origin in the scene to be 1, 2, 3. So the X coordinate is 1, Y coordinate is 2, and Z coordinate is 3. Now let's say in the game you are doing let's say in the gameplay, your player will be moving. Your player will be kind of changing the orientation of the camera from where you are looking. So let's say you want to transform the coordinates of this vertex such that you perform a rotation around Z-axis by 90 degree. So it's nothing. It could be imagined as your camera is looking straight into the scene, and your camera is tilted by 90 degrees, something like that. And then you scale by a factor of 2. So you double the size. So it can be because you are getting closer to the object, or it can be because the object itself is expanding by staying where it is. There are different ways in which the object can scale, but let's say these are the two simple operations that we want to perform, and that too for one vertex. Even in this simple scene, you just don't have one vertex. You have maybe hundreds of vertices. In an actual game scene, as I said, you will have 2 million vertices, but we are just talking about one vertex and some operations happening to this vertex how does this operation look like as a matrix multiplication? That's what we are going to look. So let's look at these two operations. So firstly, it's a common practice to add a fourth dimension to every vertex, something that looks like this. So instead of just x, y, z, you also add something called as w. So this extra dimension w will allow for these operations like scaling, rotation, translation, etc. in the form of matrix multiplication. So you don't have to individually calculate what happens to each dimensions. Rather, you can perform some matrix multiplications if you have this fourth dimension. And by default, you keep the number in this fourth dimension as 1. Okay, the value of w is by default set to be 1. So the vertex v is now represented by x, y, z, which is 1, 2, 3, and w is 1. So this is the coordinates of the vertex v. Now let's first perform the 90-degree rotation around x-axis. So a 90-degree rotation around x-axis can be represented using a matrix. Here I am denoting the matrix by R. It is represented by something that looks like this. If you have studied robotics, this will be very familiar to you. Basically, rotation around different axes can be represented as a matrix that looks like this. It will consist of cosines and sines. The more generalized format of the matrix to take into account the fact that the object can be rotated around x, y, and z, that will be a bit more complicated than this. But this is how, if you are rotating by 90 degree around z axis, this is how it will look like. So the value of the R matrix is 0, -1, 1, 0, and the rest of the things look like a unit identity matrix. Now, what do we do to rotate the rotate the vertex? We simply multiply that vertex coordinate v, which is a vector actually, by this R rotation matrix. So this is where the matrix multiplication is coming in gaming graphics. So the rotated vertex v rotated, is nothing but R multiplied by v. So this is the matrix multiplication. So matrix R for rotation is like this, and the vector v corresponding to the vertex along with the w added looks like this. And when you perform the multiplication, you get coordinates like this: -2, 1, 3, 1. I'm sure you can calculate this without even looking at the coordinates, or without even looking at the vertex or at the matrix. Because see, if this 2 is x, y, and let's say z is projecting out of the plane towards you. So I will denote it by something like this. So the z is projecting out. So x was 1, y was 2. So this was 1, this was 2, and then the z index was 3. Now a 90-degree rotation around z-axis means what happens to this vector? This vector will rotate to be something like this. And then the coordinate will be, x coordinate will be -2, y coordinate will be 1. So if the original coordinates were 1, 2, 3, after 90-degree rotation, it will become -2, 1, 3. And then you also have w, which is the additional dimension that we add. So then it will become -2, 1, 3, 1, -2, 1, 3, 1, right? So it's very straightforward, but I wanted to show this in terms of matrix multiplication for you to appreciate what is going on in rendering these scenes. Now in scaling, we also said after rotating by 90 degree, we have to perform a scaling operation where a factor of 2 is applied. So here in scaling, you can see that the factor 2 is, it's like an identity matrix multiplied by 2, but the fourth dimension is kept as 1 because here it is w is getting multiplied, so you don't have to scale the w factor. So this is the scaling matrix, and what we do is to get the final transformed vector, we multiplied the rotated vector, which was the vertex vector pointing towards the vertex, by the matrix S. S is the scaling matrix. So scaling matrix was 2, 2, 2 and the 1 along the diagonal, and then this was the rotated vector. And you get something like this: -4, 2, 6. So these three coordinates are scaled up. You can see that -2 times 2 is -4, 1 times 2 is 2, 3 times 2 is 6. The last coordinate, fourth coordinate, is unchanged. So here you get the coordinates of the vector, coordinates of the vertex as -4, 2, and 6 after performing two steps, after performing rotation and after performing scaling. Now what happens? Now we have to calculate the shading. So shading is nothing but something that happens in the presence of a light source. Because if light source is not there, this entire scene is dark. So you may be calculating the position of the vector vertex, but the vertex is not visible. Everything will look black. But in the presence of a light source, the light source illuminates the triangles. It illuminates the vertices. And by what extent is this illumination happening? The extent of this illumination depends on how strong is the light source, where is the light source placed, etc. And there are many more complex factors, but let us just consider the fact that the light source is placed at a particular location in the scene with respect to the vector, the vertex that we are looking at. So let's say the light source, although in this image, this particular image, I know that L equal to 0, 0, 10 is not the right kind of coordinate, because if this is 1, 2, 3, this cannot be 0, 0, 10, but that's okay. Let's not worry about that. Let's imagine the light source is placed at the coordinate L equal to 0, 0, 10. So X coordinate is 0, Y coordinate is 0, and Z coordinate is 10 with respect to the vertex that we were looking at, which was V equal to 1, 2, 3, right? So here what we calculate is the direction of the light. So this 0, 0, 1, 0, 0, 10 is like a vector pointing from the origin of your scene to the light source. But we want the vector that points from the direction of the vertex to the direction of the light source. So direction of which vertex? Not the direction of this vertex, direction of the transformed vertex. So for that, what we do is we do L minus V transform. So the light source is a 0, 0, 10. And from that, we subtract the transformed vertex coordinate, XYZ coordinates, and then we get something like this 4 minus 2, 4. So this is the relative positioning of the light source with respect to the transformed vertex. Now what we do is, so this step is just to show you how intensity of light can be calculated in the most simplest way. Now imagine that the camera is pointing along the z-axis. Then the normal with respect to our vertex will be 0, 0, 1 in the z direction, right? From the vertex along the z direction, you have a normal pointing, and that is denoted as 0, 0, 1. And the intensity of light is nothing but the dot product between this normal. I understand that this part is probably not as easy to imagine, but just follow with me, because it's not important how exactly the calculation of illumination of the vertex is calculated. But what is more important for you to appreciate is the fact that it's all ultimately matrix multiplication. So here you take the dot product of n with respect to this L minus V. So it will be 0, 0, 1 dot product with 4 minus 2, 4. And the dot product is 4. So now this 4 is like an index of the intensity of light at the vertex V. So, but the steps are not yet finished. So this will help us illuminate the vertex or illuminate the triangles at the vertex. And if it's like a glass material, or if it's like a very shiny material, this will, if the intensity of the light there is very high, it will shine as even more bright, part of the object. Now the last step is rasterization. Rasterization is nothing but you want to convert the 3D. So you have your vertex after transformation, it's a 3D vertex. You want to convert it into a 2D space. Why? Because your screen is 2D. You want to calculate simply on what part of your screen is this, is this particular vertex going to be placed. So now we do this mapping from 3D to 2D space. So firstly, you want to know how far your transformed object is with respect to the camera, because camera also has a particular position with respect to the coordinate system in the scene. So if the camera is at a distance d from the vertex, then there is something called as perspective projection matrix, which allows us to calculate the placement of the vertex with respect to the camera. So the perspective projection matrix P is written like this. It's like 1, 1, 1 along the diagonal. This one is 0, and here it's minus 1 by d. And here d is the distance between camera and the vertex. Let's not go into the details of all of this, because that will take us away from the point of this video. But I just want you to get a glimpse of the kind of operations in the most basic format when that happens when a vertex is being rendered. Now, if the d is let's say distance is 5, then we can apply the projection matrix to this particular transformed vector. So projection matrix is P, right? The value of this will be minus 1 by 5, and you do P multiplied by V transform. So P was 1, 1, 1, and this value will be minus 1 by 5. V transformed is this, and then that will give us this. So here you can see that the three values of these coordinates, x, y, z coordinates, transform coordinates, they are unchanged. Only the value of the w has changed now. So the original value of w that we set was 1, but now it became minus 6 by 5. Now, all we need to do is we just need to find the 2D coordinates. So we only care about xy coordinates. But to calculate the xy coordinates, you have to divide this x transformed by w and y transformed by w. So x transformed is minus 4, y transformed is 2, and W is minus 6 by 5. So X transform, the 2D value of the on the 2D plane for this particular vertex will be minus 4 divided by minus 6 by 5, right? That is this by this, which will be 20 by 6, and that is 3.33. And Y value will be 2 divided by minus 6 by 5, which is minus 10 by 6, which is minus 1.67. So this will tell you if this vertex in the 3D scene is belonging to one particular position after the two transformation, which is rotation and scaling. With respect to the camera, it will appear somewhere like this. And this on your screen is the coordinate, which is 3.33, minus 1.67. Now you might be wondering, in this picture, this does not look like 3.33, minus 1.67. Of course, it does not look like that because I took pictures separately, but this numerical calculation I created separately. The picture I just added just to give you an idea, not to show you the exact coordinates and the exact final rasterized 2D coordinates. No. So now you have successfully rendered 1 out of 2 million vertices in the scene. And these 2 million vertices make 3 to 4 million triangles, and every single one of these has to be rendered 60 times in a second. So now imagine the volume of calculations that your computer has to perform. And this is the reason why GPU is used, because all of these calculations you saw so far, matrix multiplication, vector dot product, all of these things are basically the things that GPU is really, really good at doing. It can do large volume of such calculations in parallel. And that's the reason why GPU can accelerate the graphics of your game by a significant amount. I remember while playing GTA San Andreas on my computer, this was in 2008 or something like that, 2008 or 2010. I had to reduce the resolution of the game, and I had to do a few other things to make the game run very smoothly. Otherwise, if the game graphics had to be increased, then the overall it became very slow for me to play. But I did not have a graphic card back then. Some of my friends had graphics card, and they had the luxury of playing the games like FIFA, GTA, etc. in higher resolution. It was amazing. Now things have changed much more. Now there are even more realistic games which are like 100 gigabytes, 200 gigabytes file size, which can be very easily played. So this is how in gaming the GPU completely revolutionized the entire graphics. And you might remember in some of the games, NVIDIA's logo was there in the loading screen of the game. I think it was there in GTA San Andreas, if I remember correctly. GTA San Andreas or Vice City. You could see the NVIDIA's logo when the game was loading. And in 2009, 2010, roughly around that time, deep learning researchers realized that the same GPUs which were used for accelerating gaming graphics could be also used for accelerating neural network training. And that is because if this is like a small 2 layers of a neural network, some input layer, output layer, it could be input layer, hidden layer, whatever. But I'm just showing a rough example. The operation that happens in this layer can be simply calculated using matrix multiplication. So here 2 matrices are being multiplied and a vector is being added to that. So this again can be done by GPU because it was originally designed to do this exact same thing for the context of gaming. So this is how NVIDIA completely transitioned to almost like an AI company. It was originally a gaming chip manufacturer company, like a gaming accelerator chip manufacturing company, and now it's the world's largest AI company. Just look at the stock price of NVIDIA. In 2017, it was like $3.8, and now it is like $132. It has increased by a huge amount. I remember actually talking about NVIDIA with some of my friends, even at this point, and I regret not buying NVIDIA stocks when it was here. I thought it was overvalued even at that time. There was a lot of overvaluation in general happening, like around right after COVID, like when the interest rates were very low. So federal interest rates were very low. So this was a great time. But then NVIDIA has peaked even beyond that. At one point, its market cap was even above Apple. That it was the largest company in the world in terms of market cap. So this is how NVIDIA became what we see today. And in 2022, right, NVIDIA sold this. So it has 2 types of GPUs clearly. One is these gaming GPUs, graphics card, right? It sold around 30 million of those desktop GPUs. These are primarily meant for gaming, not very expensive, $200 to $1,500. So it's like what, 16,000 rupees to maybe 1.5 lakhs, something around that. And the other type of GPUs are data center GPUs. So these are much more expensive, $10,000 to $40,000. I had seen news that said Facebook Meta had purchased a lot of these GPUs in bulk at some point. I saw that in 2023, NVIDIA sold 0.5 million of such GPUs. So let's just calculate the number, right? So this is 30 million multiplied by roughly $1,000 on an average, let's say. So that I don't know if they sold 30 million multiplied by this will make it 30 billion. I'm not sure if NVIDIA made $30 billion on gaming GPUs. Maybe they did, maybe they did not. I'm not sure. I'm assuming that each gaming GPU costs around $1,000. Here you can see that when you do a calculation, it's like let's say $20,000 per GPU on an average multiplied by 0.5 million. So 0.5 million multiplied by 1,000 will be 0.5 billion. Multiplied by 20 will be around 10 billion. So on the order of magnitude, NVIDIA made around 10 billion from this and around 10 billion from this. I'm not sure if this is true. This calculation is true, but we can check that. But these data center GPUs are primarily meant for training large language models, neural networks, etc. And this meme, I'm sure you must have seen when everyone is digging for gold, which is like these companies like Microsoft, Google, Meta, OpenAI, they are all selling AI products, AI digital products like trained large language models for free or for a certain subscription fee. NVIDIA is, so they are digging for gold in this AI age, literally. And NVIDIA is at the same time selling shovels. Shovels are the engines that are used for training the AI models, which are GPUs. So that makes NVIDIA the biggest AI company in the history. And I'll stop this video with this particular meme. And it's really fascinating to see the way NVIDIA has grown. And I think it's only going to increase the demand for these chips because there is only finite quantity of chips available. There was even a chip shortage at some point. So its value is going to increase. I think NVIDIA's value is going to increase really. Many of my friends who had invested in NVIDIA by like a huge amount, they have made a lot of money if they have not sold their stock already. But that's it. I hope you understood how GPUs help in accelerating the gaming as well as in AI. And especially, I hope you understood how GPUs help in matrix multiplication, which is the cornerstone of what happens in AI model training as well as in gaming graphics rendering. With that, let's conclude the video. Thank you so much. And we'll see each other again in yet another video. Take care until then. Bye.